Hello. In this video, I will go over the second half of the section on lines and planes. We will cover a variety of odds and ends, different types of circumstances that you might encounter with lines and planes, combinations of lines and planes, just a lot of different examples. Okay, so we'll start off with the first kind of odd and end that we need to discuss is the synthetic form of a line. The synthetic form of a line can be found by taking the parametric form and solving for t. So for example, if we had in 2 dimensions, we have x equals x naught plus at and y equals y naught plus bt. Or in 3 dimensions, we have x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. So if you take the 2-dimensional equation and you go through and you solve for t in both equations and set them equal, you'll generate the synthetic form. And the same thing is true for these 3 equations, except you have to solve for t for 3 equations. So let's just go ahead and do that, right? So if we're going to solve for t in this first equation, we would end up getting x minus x naught equals at, and then x minus x naught divided by a equals t. And then if we do the same thing for the second equation, we would get y minus y naught equals bt, y minus y naught over b equals t. And then set the 2 t equations equal, and you generate x minus x naught over a equals y minus y naught over b. And that is the synthetic form of a line. It's used much more rarely than the parametric form, but it is something that you do encounter. As far as the 3-dimensional version, again, solve for t in each one of these, set them equal, and you'll end up with x minus x naught over a equals y minus y naught over b equals z minus z naught over c. So how does it work? It works in the same way that the parametric form works, and that is that if you have the point and the vector, in the parametric form, you plug the point in here, and you plug the vector in here. If you have the point and the vector in the synthetic form, you plug the point in here, and you plug the vector in here, right, the direction vector. So for example, let's say that you went through and you solved a problem and you had you wanted to generate the equation of a line. With a point of 1, -3 and a direction vector of 2, 5, then the synthetic form, you'd have x minus 1 divided by 2 equals y plus 3 divided by 5. Right, so you take the point, put the point values here, and you have to subtract, don't forget to subtract, and then you divide by the vector values. Okay, so that is the synthetic form of a line. Okay, next, let's go through and do a couple different types of line problems that you might encounter. So find the equation of the line passing through -1, 3, 4 that is parallel to the line x equals 3t, y equals -5t, and z equals 1 plus t. So when you're asked to go through and find the equation of a line that is parallel to another line, the way that you could think about the information that you have is you have a line, right? And that line is made up of a point and a direction vector. Okay. And then you're asked to go through and find a line that is parallel to it, and you just have the point. Okay, so if you're going to go through and generate the equation of a line, what do you need? You need a point and a direction vector. So we already have the point, right? We just need to get the direction vector out of the line that's parallel. And the way that you do that is you just go ahead and use the direction vector for the line that we're parallel to. Okay, so the way that you could think about it is that they gave us this line. We want to find the line that's parallel to it. Well, it's good. That's what the line is going to look like that's parallel to it. And so we can just use V for our new line. And so what is the direction vector? You just have to pull it off of the parametric form of the line here. And so that would be V equals, right? So it's the numbers that are multiplied by t. So it's going to be 3, -5, 1. And then take that, combine it with our point, and we end up getting x equals -1 plus 3t, y equals 3 minus 5t, and z equals 4 plus t. So one consequence of this problem, if you think about it, is it implies that parallel lines have parallel direction vectors, and that is a true fact, right? Anytime that you have two lines that are parallel, the direction vectors will be parallel. So that's just a fact that it's good to keep track of. Oops. Okay, and now let's try another. So the next one we have, find the equation of the line. Passing through zero, 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 the origin. That is perpendicular to the vectors 1, -2, -1, and -2, 1, 4. Okay, So the information that you have here is so anytime you're trying to go through and find the equation of a line, you need a point and you need a vector. So they gave us a point, a direction vector. They gave us a point, but they did not give us a direction vector. However, what they told us is that the line that we're trying to create is perpendicular to two given vectors. And so one thing you could do, you could just draw yourself a little picture. So let's say this is 0, 0, 0. And we want a line that is perpendicular to these two vectors. So let's just draw two vectors. Now, these vectors are not parallel, so you could just go through and just draw any two vectors. So we'll say this is the first one, which we'll call, let's call it x. And then this is the second one, and let's call it y. Okay, so anytime you have two vectors that are not parallel like this, what you can do is you can go through and you can use those two vectors. And again, the way that I drew them here, they both originate at the point where we're going to find our line. Anytime you've got two vectors, you can go through and you can use those two vectors to create a plane. Okay, and so this is a quadrilateral, but you have to use your imagination that it just extends in every direction. So it's like a flat piece of paper that forms a plane. And so if we want to find something that is perpendicular to these two vectors, that object would end up being perpendicular to the plane. And so we could go through and draw. This is the line that we're trying to find, right? Is the line that ends up being perpendicular to that plane that defines those two. All right, so we would get right angles, right, with both of those. Well, so how could we go through? And so we have the point, but we need this vector. So how could we go through and find v given x and y? Well, if you're tasked with going through and finding a vector that is perpendicular to two given vectors, that is exactly what the cross product is for. That is the principal use of the cross product. So if you're not aware of that, then that's something to memorize. So we need to go through and find x cross y. So that's going to be I, j, k. 1, -2, -1, -2, 1, 4. I times -8 minus -1, so that's going to be plus 1, minus j, we get 4, minus 2, plus k, 1 minus 4. And we end up with -7i. And what are we going to have here? Minus 2j, and then minus 3k. So that is going to be our vector that's perpendicular to these two. And so that's going to be the direction vector for the line that we're trying to create. And so once we've got that vector, we then will have the point for the line, and we'll have the direction vector for the line. So once you've got those two, you combine them in the parametric form, and that gives you the answers. So we'll have x equals 0 minus 7t, y equals 0 minus 2t, and z equals 0 minus 3t. And then, of course, you can simplify this. And that is how you go through and find an equation that is perpendicular to two vectors. The equation of a line. Okay, another situation that you may encounter. You may be asked to go through and find the intersection of a line and a plane. Okay, so if you're asked to go through and find the intersection of a line and a plane, the way in which you do that is you'll notice that in our line definition, we have an XYZ. In the plane definition, we have an XYZ. Take these three XYZs and plug them in, and then you can go through and solve for T, and that will give you the T value for where the line hits the plane. So let's go through and do that. All right, so we're going to have 3, and then x is 1 plus t, so plug that in, minus 4, and then z times 4 minus 2t equals 2, and that's going to get us 3 plus 3t, 8 plus 12t, oops, and then 4 minus 2t equals 2. And if you combine 3t, 12t, and negative 2t, we're going to get 13t. 3, 8, and 4, we combine to get 15. And then 13t equals negative 13. T equals negative 1. And then once you have your t value, in order to find the actual point, right, the point of intersection of the line and plane, you need to take your t value and plug it in to your line, and it will generate a point. Okay, so if we do that, we're going to get x equals 1 minus 1, right? We're plugging in negative 1 for t. And then y equals negative 2 minus 3 times negative 1. And then z equals 4 minus 2 times negative 1. So 1 minus 1 is 0. Negative 2 plus 3 is 1. And then 4 plus 2 is 6. A good question might be, what happened? How could you tell if a line and a plane did not intersect? Well, what will happen is if you go through and plug this in, then you'll get no solution. Okay, so you will not end up getting a t value if it is not possible. Okay, so that's how you go through and find the intersection of a line and a plane. Next. The next situation we're going to look at is determining, how do you determine whether lines are parallel, skew, or intersecting? So what do these three things mean? Let's just talk about them for a moment. All right, so parallel, we know what parallel lines are. You go through and you have two lines next to each other. Right. The thing that will help us in terms of understanding these three definitions is if we think about parallel lines are where you could go through and put a plane on those two lines. So if you think about this as kind of two pieces here, two supports, if you will, you could lay a piece of paper down on top of them, and that would form the plane that contains those two vectors, right? You see that? So you've got, if you have two lines that are parallel, they're two lines that sit on a plane, or a plane could be sat upon them. Okay. Intersecting lines are where you have two lines that intersect. That kind of makes sense. Okay, however, the thing about intersecting lines is that they also sit on a plane, right? If you had two lines that intersect, you could go through and draw a plane. You could like set a piece of paper down on top of those two lines where they intersect, and that would be your plane, right? So both parallel lines and intersecting lines so they both sit on a plane, right? So you've got a plane where you've got two lines that don't intersect, and you've got a plane where you've got two lines that do intersect. Skew lines, and the reason I describe it this way is that what skew lines are is they're two lines that sit on parallel planes. Okay, so it's a little difficult, maybe easiest to visualize it with a three-dimensional coordinate axis. Okay, so let's say that we have one of our planes is the XY plane, and you have a line that goes that way, and then directly above it, you have a second plane that is parallel, and that has another line on it. And so because these two lines lie on parallel planes, they never intersect. These are called skew lines. Okay, and these are the only three possible types of situations with two lines. Either two lines are parallel, and then they sit on one plane but never intersect. They're intersecting, so they sit on one plane and they do intersect, or they're skew. They sit on two planes that are parallel. Those are the only three possibilities. And you can play around with this, with your arms in the room, try and make your arms do different things. But if you have two lines that never intersect, then you could go through and have them represented on parallel planes. Okay, so that's the idea behind the three different cases. Two of them exist on one plane, the third one exists on two separate planes. So in order to go through and to do a problem where you're asked to calculate this, we need to figure out what represents each one of these scenarios. So how do you tell which case you have? All right, so parallel is the easiest of the three. We've already discussed that. Parallel lines have parallel direction vectors. Okay. And then the second is figuring out, so assuming it's not parallel, so you've got to check that box, then in that case, it's either going to be intersecting or skew. The way that you tell intersect versus skew, what you can do is you can try and find a point that will satisfy both of the two lines, right? That's what it would mean to have an intersection. And in going through and trying to do that, if you're successful in finding a point that satisfies both lines, then the two intersect. If you end up failing as you try and accomplish that, then the two lines are skew. Let's do say this both line equations. If you're successful, the lines intersect. If not, skew. So let's go through and try a couple examples. Let's say that line 1 is in synthetic form. And line 2 also in synthetic form. Okay, so the first step is to check, are the two lines parallel? Now, again, the way that you check the two lines are parallel is you look at their direction vectors and you try to determine whether their direction vectors are parallel. If their direction vectors are parallel, that means that one is a scalar multiple of the other. Like that, it means that the two vectors have the same ratios between the components. Okay, so in this case, for example, like if we look at the first component, see how, so again, the vectors for synthetic are in the denominator. So this would be A, B, C, A, B, C. So if we look at this, we can see that this component is double that one. This component is double that one. So far they do have the same ratio, right? So this one is -1 times that one. This one is -1 times that one. However, the third does not meet that criteria. If this had been a 6, then the two lines would have been parallel. Okay, so they would have had the same ratio. 1 to -1 to 3 is the same ratio as 2 to -2 to 6. Okay, this is just double that one. Okay, however, that's not the case. So these are not parallel because of that 7. All right, so thus the two lines are not parallel. So once you determine that they're not parallel, the next step is to go through and try and find a point that will satisfy both equations. How do you do that? All right, well, first let's go through and take the two and translate them to parametric form, which is a more useful form. So we're going to get x equals t, y equals 1 minus t, z equals 2 plus 3t. So that's line 1. And then line 2, we're going to do x equals 2 plus 2s, y equals 3 minus 2s, and z equals 7s. Why use t's here and s's here? It's important to have different variables because these two lines they're traced out over different values, right? So if you go through and you plug in values for t, you don't want to use the same values for t here and here because those could be, you could have different t values at different points, right, based upon these, right? So if you go through and have where t is 0 for this, that might go through a point where for this line, that would not be at s equals 0, or if you use t here, it wouldn't be at t equals 0, it might be at t equals 5, right? So you need to have two different values so that this could go through a point at t equals 0, and this could go through the point at s equals 5, right? Whereas if you use the same variable, then it would be confusing. So once you've gone through and you've represented the two equations, the way that you go through and try and find a point that satisfies both of the two equations is to take the x, y, z values and set them equal. So we're going to get 2 plus 2s equals t, and 3 minus 2s equals 1 minus t, and 7s equals 2 plus 3t. Okay. And so the next step when you're going through, now this is now a system of equations. The next step we want to do is to go ahead and solve the system. And this is a little bit unusual for systems of equations. Normally, if you have two variables, you have two equations, right? But that's the way that these problems work, is that you're going to have three. And in order to solve it, what you want to do is you want to pick two of the equations and solve it, and then just test your result on the third, right? Assuming that you were successful in solving the first two. So let's go ahead and pick two and try and solve this and see what happens. Right. So one of the things you could do is you could try picking these top two, because you can see some nice stuff happen. See how the 2s and negative 2s, right? So let's try that. Okay, so if you take these two and you write them off to the side, right? And the way that we solve this, we could solve it by eliminating variables. We could solve it by adding the two, and the s terms would cancel and we'll get 5. The t terms would cancel and we would get 1. Oh, look at that. All of the variables canceled and we got something that's false, right? So when you're solving a system of equations and that happens, that means that there's no solution. Okay, so in our goal of trying to find a point that would satisfy this equation and satisfy this equation at the same time, right, which we tried to accomplish by setting the equations equal, we ended up getting a false statement. We ended up getting that there's no solution, right? So that's what happens when the two lines are askew, right? If it's possible to go through and find a point that satisfies both, you'll end up going through and solving the system, and you'll get something that's true, and you'll get all three, something that will make all three of the equations true. When that happens, that tells you that the lines intersect. If you try and solve it and it doesn't work, then that tells you that there's a skew. So right here, that's enough information. The lines are skew. Now, this is actually a little bit unusual to have this happen this quickly, where on the first step, the variables just cancel and you end up getting no solution. So let's go through and try using the bottom two so you can see what happens in a more conventional problem where you're going to end up with skew lines. Let's just kind of draw a line here and go off to the side here, and we're going to pick these two instead of picking the top two. All right, so if you pick the bottom two, so let's put those together. So we're going to have 3 minus 2s equals 1 minus t, and 7s equals 2 plus 3t. Okay, so let's say we want to eliminate the t's, so we'll multiply the top guy here by 3. So that gives us 9 minus 6s equals 3 minus 3t. And we've got 7s, 2 plus 3t. And then we go through and add them, and what happens? So we're going to get 9 plus s. The t's cancel, equals 5. So s equals negative 4. And then once you have s is negative 4, you can then plug it into one of these equations to go through and get t. So let's plug it into this guy here. So if we do that, we're going to get, let's go this way. We're going to get 7 times negative 4 equals 2 plus 3t. And so it's negative 28. 2 plus 3t. Negative 30. 3t. And then t equals negative 10. So you'll notice we were successful in going through and solving the system of the two problems that we chose, the bottom two equations. We successfully found a point that actually will work for both y and z. Okay, so now let's see what happens if we take that point and test it on x. All right, so you could take t equals negative 10 and s equals negative 4, and you could plug it into these bottom two equations, and it will give you a y and a z coordinate. And so the question is, does it work on x? So let's try this, take this and plug it in. And so this is the equation for x. So we're going to have 2 plus 2 times negative 4 equals negative 10, right? So take your s value, plug it in, take your t value, plug it in, and that's what happens. So we get 2 minus 8 equals negative 10. So we get negative 6 equals negative 10, right? And that is not true. So that's not true. So there's no solution. And this is this is, you can tell that the two lines are skew. This is the more typical case where you go through and you pick two equations, you actually get a t and an s value, and then you end up getting that the two lines are skew. Right? So the way that I interpret this is if we kind of go back to our picture here, right? We went through and we found, so obviously these two lines do not represent the lines that we were just doing, right? This is just a generic picture, right? But essentially what we did is we found a set of coordinates that work, that are directly above or below each other in this picture, and then this ended up not being the same. And so that's the way that I interpret the skew lines, is when you go through and you solve two of the equations, you end up getting something that works for two of the variables, that ends up getting you points that are directly across from each other on the parallel planes. And so in this hypothetical case, now again, this picture does not represent but what we ended up with these two lines. But in that case, if it did, then you could think about it like this line is at z equals -6, and this line is at -10, and that difference apart, that is what prevented them from intersecting, right? If you just shifted this plane downward so that it landed on the other one, you'd shift it down 4, and that would make it so that the skew lines are now intersecting lines. Okay, so that is how you go through and find parallel, intersecting, or skew lines. Next, let's move on to planes. Find the equation of the plane that passes through -4, -5, 6, that is parallel to the plane (2x plus y minus 4z equals 7). Okay, so when you're asked to go through and find the equation of a plane, you need two pieces of information. You need a point and you need a normal vector, right? So in this problem, they say find the equation of a plane that passes through the point. So they gave us the point, but they did not give us the normal vector. Instead, they gave us a plane that is parallel. Okay, well, let's draw ourselves a picture and see if we can wrap our heads around what the information that they gave us is. Okay, so we have a plane. That they gave us, all right? Let's say that's 2x plus y minus 4z equals 7. They asked us to find the equation of another plane that is parallel to it. All right, well, parallel planes are just like parallel lines. They're planes that never intersect. So this plane is going to be directly above that one so that they never touch. Okay, and they gave us a point that lies on this plane here. It's -4, -5, and 6. So this is the information they gave us. If we go through and draw the normal vector, right? So the bottom plane here is the one that's parallel. What would the normal vector be? Well, we could just pull that off of the plane equation here. That's going to be 2, 1, -4. What would that look like? Well, a normal vector is orthogonal to the plane. It forms a 90-degree angle with the plane. So it would come directly straight up off of the plane. Well, if two planes are parallel, if this normal vector comes directly up off of the plane and forms a 90-degree angle with this one, what angle do you think it forms with this one? It also forms a 90-degree angle. Okay, Why is that? Well, the way that you could think about it is if you took this plane and shifted, if they're parallel, you could take this plane and you could shift it downward. And what would happen? It would land right on this plane. It would become this plane if you just shifted it downward. And so if by shifting this plane downward, it landed right on this other plane and became this other plane, then they both have to be orthogonal to the normal vector, right? So just moving a plane up and down, okay, in the direction of the normal vector is not going to change the angle that the plane forms with that normal vector. So that's the idea, right? Basically, another way of saying this is that parallel planes have parallel normal vectors. So what we can do is we've got a point, we need a normal vector, you can just use the normal vector from the other plane. And once you've got the normal vector and the point, you just plug the two in to the plane equation. So we're going to take 2 times x minus -4, so that's going to be plus 4, plus 1 times y minus -5, so that's going to be plus 5, minus 4 times z minus 6 equals 0. And that's the answer. Okay, that's how you go through and find the equation of a plane that's parallel to a plane. Okay, next, find the equation of a plane containing the points 1, 2, -3, -1, 0, 4, and 3, -2, 1. Okay, so let's again kind of just draw a little picture for ourselves. We have a plane. We have 3 points that are on there. And we're asked to go through and find the equation of that plane. Let's go ahead and just label the points. So we'll say this is P, this is Q, this is R. So this one we'll say is P, Q, and R. Okay, so anytime you're asked to go through and find the equation of a plane, you need 2 pieces of information. You need 1, a point, and 2, a normal vector, right? So in this case, they gave us 3 points, no normal vector. So we need to somehow take these 3 points and turn them into a normal vector. So how could we do that? Okay, well, the way in which we could do that is we could take the points and we can turn them into vectors by subtracting the coordinates, right? So we could go through and create vector PQ, and we could create vector PR, right? So vector PQ would equal -1 minus 1 is -2, 0 minus 2 is -2, 4 minus -3 is 7. And PR, 3 minus 1 is 2, -2 minus 2 is -4, 1 minus -3 is 4. Okay, once we have 2 vectors, now look at those 2 vectors. Because we had the points that are on the plane, by subtracting the coordinates, we created vectors that are on the plane. So what we have is we have 2 vectors that lie on the plane, neither of which is parallel to the other. And what we would really like to have is we would really like to have the vector that is orthogonal to both of those, because the vector that's orthogonal to both of those vectors will be the normal vector, right? The vector that comes directly up off the page will form a 90-degree angle with both of those two given vectors, right? And so how do we go through and find a vector that is orthogonal to two given vectors? That's what the cross product is for. So the normal vector is going to equal PQ cross PR. So we get I, J, K, -2, -2, 7, 2, -4, 4, I times -8 plus 28 minus J. We're going to have -8 minus 14. So that's going to be -22. And then we're going to have 8 plus 4, and that's 12. So this simplifies to 20I plus 22J plus 12K. Now we have the normal vector. Once you have the normal vector, to go through and find the equation of a plane, you just need a point and the normal vector, and then put the two together into the plane equation. So you can pick any of these 3 points that you want. It doesn't matter which one you use. I'm just going to use the first one here. So we're going to have 20 times x minus 1 plus 22 times y minus 2 plus 12 times z plus 3 equals 0. And that is the answer. Okay, next. How do you determine whether planes are parallel, perpendicular, or neither? Okay, so we've already discussed parallel planes. Parallel planes, you go through and draw yourself a picture. Parallel planes are directly above and below each other. That picture is terrible. They're directly above and below, or to the left and to the right, or front and behind. And if you go through and take the normal vector for one and just draw it, it passes directly through the other. And if it's normal to one, it's going to be normal to the other. So that gives us parallel lines, or parallel planes, perpendicular planes, so perpendicular planes are when you have two planes that are perpendicular. So if we went through and drew a plane, let's try that again. Let's say that's a plane, and then we have a plane that's perpendicular to it. So planes that are perpendicular, 90-degree angles. Okay, yeah, that's not so good. Let's try that one more time. You know what? Let's just use the straight line tool. That's cheating, but it works. Okay, so we've got a plane. Think of this as the floor. We've got another plane. Think of it as a wall. There's a 90-degree angle. Okay, if you were to go through and draw the normal vectors, so let's say we've got the normal vector for this one, right? It comes 90 degrees up off of the floor. Okay, and you have the normal vector for this one, and it forms a 90-degree angle of the wall, then what is the angle that's going to be formed where the two normal vectors, assuming you position them such that they intersect, what would be what angle would you end up getting? And the answer is you're going to get a 90-degree angle there as well. The way that you could prove that to yourself is that if you took this normal vector and you ended up shifting it downward, it's going to land on the other plane, right? And so since if you took this vector and shifted it downward and it landed on the other plane, the normal vector to that plane has to be 90 degree, that has to be a 90-degree angle to any vector that's on the plane. So if you shifted this down, it would have to be a 90-degree angle with this vector here. And just shifting it downward is not going to change the angle between the two vectors. Hopefully that made sense. In any case, perpendicular vectors, perpendicular planes have orthogonal normal vectors. I didn't write it up here because we've already discussed it, but parallel planes have parallel normal vectors. And then finally, the third case is neither. And so for the neither case, we can go through let's say we have a plane, and then we have another plane that is not parallel or perpendicular, right? It's like a laptop that's partway closed. How do we tell if we have this scenario? Well, what we do is we check for these two, and if it's not parallel and it's not perpendicular, then it's neither. So that's the way that you're going to go through and test, right? If normal vectors are not parallel or orthogonal, then the planes are not parallel or perpendicular. It's neither, the neither case. Okay, let's see this in action. So let's say we have 9x minus 3y plus 6z equals 2, and 2y equals 6x plus 4z. And the question is, these are two planes. Are they parallel, perpendicular, or neither? In order to answer that, the first thing that we check for is, are they parallel? And the way that we check for that is we want to compare their normal vectors. So let's go through and rewrite this second one so that it's in the form where we can just read off its normal vector. To do that, move the x and z to the same side as the y. So we're going to have negative 6x plus 2y minus 4z equals 0, right? And so here's our first plane, here's our second plane, and the normal vector for plane 1 is 9, negative 3, 6, and the normal vector for plane 2 is negative 6 to negative 4, and the question is, in order to tell whether vectors are parallel, they need to be scalar multiples of each other. So what that means is that there's a number that you could multiply by a scalar that you could multiply by all three components that would turn one into the other. So is there something that you could multiply by -6 to turn into 9, by 2 to turn into -3, and by -4 to turn into 6? And the answer is, if you think about it for a minute, yes, there is. You could multiply by -3/2. So this becomes this if we multiply by -3/2. So they are scalar multiples of each other, and thus the two are parallel. These are parallel planes. All right, let's try another one. Okay, so we have two planes here, and we're asked, are these parallel, perpendicular, or neither? In order to figure that out, we need to be able to read off the normal vectors. So the normal vector from plane 1 here is going to be 5, 2, 3. For plane 2, we need to rewrite it. So it's going to be -4x plus y plus 6z equals 0. And then the normal vector for plane 2 would be -4, 1, 6. And then in order to check, are these parallel, perpendicular, or neither? Well, are they parallel? Well, that was the case that we just had in the last problem. Is there a number that you could multiply by all three of these components that would turn it into the other three components? And the answer to that is no, right? So 6, you'd multiply by a half to turn into 3. 1, you have to multiply by 2 to turn into 2. So those are not the same number. So clearly that's not going to work. All right, so not parallel. The second thing you test for, are the two planes going to be perpendicular? That happens when the two vectors are orthogonal. So is there an easy way for us to tell if two vectors are orthogonal? Yes, there is. All right, that is the dot product. That is one of the principal uses of the dot product, is to go through and tell whether two vectors are orthogonal. And you go ahead and calculate the dot product, and if the dot product is 0, then they are orthogonal. Okay, and the dot product, we do component-wise multiplication, and then we add the results. We're going to do 5 times -4, that's -20. 2 times 1 is 2. 3 times 6, 18. -20 plus 2 plus 18 does equal 0. Thus, the two normal vectors are orthogonal. Thus, the two planes are perpendicular. If we had not gotten 0, what would that have told us? It would have told us that the two planes are neither parallel nor perpendicular. Okay, next, how do you find the line of intersection of two planes? And let's say the planes that we have are -2x plus y minus 3z equals 5, and x plus 4y plus 5z equals 2. Okay, so the important thing when you're asked to go through and do something they haven't done it before is to draw a picture. So let's see if we could draw a picture. So there's a plane, right? So we'll go ahead and label this and say, hey, this is plane 1. We'll say this is plane 2. We'll say that's plane 1. Let's go through and draw plane 2. Okay. And so we're asked to go through and find the line of intersection. So this is plane 1. We'll say this guy's plane 2. So the line of intersection is going to be that line, the red line. Oops, I want that to be black. That's plane 2. Okay, so how do we go through and do this, right? Well, the first thing that you need to realize is that the line here, the red line, it's on both planes, right? If it's the line of intersection, the red line is on plane 1 and it's on plane 2. And since it's on both planes, what is going to be true about the line relative to the normal vectors? The line is orthogonal to both normal vectors. All right, so think about that, right? So what does it mean to be a normal vector? The normal vector is orthogonal to any vector that lies on its plane. All right, so the normal vector for plane 1, and you could try and draw it, although at a certain point your picture just gets to be kind of a mess, but we could just kind of sketch something in here. So let's say that's the normal vector. All right, then any vector that's on the plane is going to be orthogonal to this. And what is true about this line? It's on the plane, it's on P1, right? So that line is going to be orthogonal to that normal vector. Now let's erase it. That's just a fact we need. Okay, and now what about the line relative to plane 2? Well, you could try and draw a normal vector to plane 2. I don't know, let's say that's the normal vector for plane 2. Okay, well, what's true about this line? That line's on plane 2. Since the line is on plane 2, it must be orthogonal to that normal vector 2. So what we have is we have a line that is orthogonal to 1, 2 normal vectors. Okay, if you have something that you're trying to find and it's orthogonal to 2 other things, how could you find it? The answer is the cross product. And in particular, the cross product is not going to get us the line here, but it will get us a vector that is along that line. Okay, so now that we know that, let's go through and actually find that vector. All right, so the normal vector for line 1, let's just write it down here below. The normal vector for line 1 is going to be -2, 1, -3. The normal vector for line 2 is going to be 1, 4, 5. And then we can go through and calculate n1 cross n2. And that's going to be our direction vector. So that's going to be v. We'll have I, j, k. -2, 1, -3, 1, 4, 5. This equals I, and then we're going to have 5 minus -12. That's 17. Minus j, we're going to have -10 plus 3. That's -7. And then k, -8 minus 1. And so from that, we're going to end up getting 17i plus 7j minus 9k. Okay, so we have the direction vector for our line. However, is that enough to go through and define the equation of a line? Is the direction vector alone enough? The answer is no. To go through and define a line, you need a direction vector and you need a point. So we need to go through and find a point. Okay, so to do that, let's just get rid of this. And the way that you can go through and find a point is we're just looking for a point that we could plug into these two equations that would make both of them true. So let's just rewrite the equations over here off to the side. So we're looking for an x, y, and z that we could plug in that would make both of the equations true. All right. The easiest way to go through and find such a thing is to actually go through and plug in a value. That might seem a little bit unnatural, but it's okay. So in particular, in this case, I'm just going to plug in z equals 0. So if I plug in z equals 0, what it does is it corresponds to the xy plane. And so essentially what I'm finding is I'm finding the part of this plane that lies on the xy plane, and I'm finding the part of this plane that lies on the xy plane. And then I'm looking for where those two parts, which are going to be lines, I'm looking for where they intersect. Now, how do I know that both of these planes hit the xy plane? It's because of this vector here. The vector, if this did not hit the xy plane, okay, it would have no k component. Okay, so the fact that it has a k component tells me that it's moving up and down, and so it's going to hit the xy plane. However, it would be very unusual if you were going through and solving one of these line of intersection problems to only get two components here. And so typically you'll get all three, and what you can do at that point is you can just set one of the three variables to a number. And I recommend setting 1 to 0 because that just makes it the easiest. Okay, so what we're going to do is we're just going to go ahead and say, we want to find the point where z is 0. If you do that, it kills these terms here, and you end up with -2x plus y equals 5, and x plus 4y equals 2. And then we can solve this by multiplying this bottom guy by 2. So we're going to have -2x plus y equals 5, 2x plus 8y equals 4. Add them, you get 9y equals 9. Y equals 1. Take that, plug it in to this guy here, and we'll get -2x plus 1 equals 5, -2x equals 4, x equals -2. And we got three values that if you plug them into these two equations, it will make both of them true. Right? So z equals 0, it kills these two terms. So it just has to satisfy what's left, and you know that these two satisfy what's left. So the point that we ended up with that will satisfy both equations is -2, 1, 0. All right, and once you have a normal vector, once you have a direction vector for your line and you have a point for your line to go through and find the equation of the line, you take the point and you take the direction vector and you put them together into the parametric form. So you're going to get x equals -2 plus 17t, y equals 1 plus 7t, and z equals 0 minus 9t. And that's your answer. Okay, so that's how you go through and find the line of intersection. And then finally, a classic application problem that you encounter in this lines and planes section is to go through and find the distance between a point and a plane. Now, there's a reason that this classic application is in this section, which you will see as we go through and do a problem. However, what we're going to do first to do the problem is really the most important part, and that is we're going to derive the formula. There's a formula for finding the distance between a point and a plane, and the formula is deriving the formula is what's interesting and worth doing. Actually, just using the formula is not that interesting. So let's just say our point. We'll say our point is P, and let's say it's x1, comma y1, comma z1, and let's say our point is ax plus by plus cz equals d. All right, so we're given a point and we're given a plane, and we're told go through, find the distance between the point and the plane. How do you do that? In order to do that, you first need to start off with a picture. Let's say that we have a plane. Okay, that's this. We're given that. We're also given a point. Let's say we've got a point out here. And here's our plane. So it's that guy right there. Okay. So we can go through, and if you have a plane equation, even if it's in this form where you can't easily just read off a point, you can always go through and find a point by setting 2 of the coordinates to 0 and just solving for the third. So we're guaranteed that we could go through and find a point that's on the plane. Let's call that point x naught, y naught, z naught. So we go through and we find a point that's on the plane. Let's say that's that point right there. Okay. And what's going to be true about that point? Since that point lies on the plane, if I take that point and plug it into this equation, it will make the equation true. All right, that's going to be important later on. But if you take this point here and plug it in, it works for the equation. Okay, so once we've got this picture, the next step, oh, and one other thing, with the plane, we do have the normal vector. The normal vector is going to be the numbers that are multiplied by x, y, and z. So it's going to be a, b, and c. And what we're going to do is we're going to take that normal vector and we're going to draw it in a particular spot. We're going to draw it right here so that it passes directly through the point. Okay, now I want to be clear here about that normal vector. You could put it anywhere. All right, you could put it here or here or here or here. We want to pick the spot that will cause it to pass through the point. Now, it's not going to stop directly here on the point. That would be very unlikely. The normal vector, the length of the normal vector, it might be short of the point. It might be past the point. All right, we're going to make sure it's long enough. We're going to go ahead and draw it so that it passes through the point, just like that. Okay, and so this is our picture. We have the plane. We have a point that's on the plane that we could plug into the plane equation that would make it true. And then we've got our point, and we've positioned our normal vector such that so that the picture looks like this, so that it passes right through. Okay. Once you've got this picture that takes all of our information and compiles it, the next step we're going to go through and we're going to define this vector. All right. So what would that vector be? Well, it's the vector that starts at x naught, y naught, z naught and terminates at x1, y1, z1. So it would be the vector. If we went through and labeled this point Q, it would be QP, and that would be x1 minus x naught, y1 minus y naught, and z1 minus z naught. And so we get this picture here. Now take a look at that picture. We're asked to find the distance between the point and the plane. What is that? That's going to be this distance here. That's what we want. We want to know, what is this? Okay, well, if you just took this picture and you just rotated it so that you were looking sideways at the plane, what would you see? You'd have the normal vector. You'd have the point. You'd have this point. And then the plane in our picture here would just be a line because we're looking at it sideways, right? This is assuming we looked sideways at this picture. We looked at it from this. We looked at it from this perspective, this angle. We looked at it this way. That's what you'd see. Okay. And what we want to know is we want to know the distance between the plane and the point. That's this distance here. On our picture, that's going to be this distance. So how could we go through and find that distance? Where this is the normal vector, and this vector here is QP. Well, hopefully this picture looks similar to a picture from a previous video that you watched. And in particular, that's the video on projections, right? So what we're interested in, this distance here, this would be the length of the projection of QP onto N. Okay, right? If you took QP and you just projected it, it would give you just this. If you took QP and you projected it onto N, it would give you just that. And we want the length. So the length, that's going to be the component of QP onto N. So what is that? That is N dotted with QP divided by the length of N. And what is that? N, we said, is the normal vector. That's A, B, C. QP is right here above. X1 minus X naught. Y1 minus Y naught. Z1 minus Z naught. What is the length of N? It's the square root of the component squared. And if you calculate this dot product, it's going to be A times X1 minus X naught plus B times Y1 minus Y naught plus C times Z1 minus Z naught all over the square root of A squared plus B squared plus C squared. And then if you went through and distributed this, what's going to happen? We're going to have AX1 plus BY1 plus CZ1. And intentionally, I'm putting those first. And then we're going to have minus AX naught minus BY naught minus CZ naught all over the square root of A squared plus B squared plus C squared. Okay, well, don't forget, what did I say earlier? This point lies on the plane. That means it has to satisfy the plane equation. It has to work if you plugged it into the plane equation. Okay, well, what would you get if you took this point and actually plugged it in? Right, well, we can figure that out, right? So it's going to be ax naught plus by naught plus cz naught, right? That's just taking this and plugging it in equals d. Since this point is on the plane, it has to satisfy the plane equation. So you end up getting this. Well, take a look. You've got negative ax naught minus by naught minus cz naught. And so the last step here, which we kind of ran out of space, but it's going to equal ax1 plus by1 plus cz1 minus d all over the square root of a squared plus b squared plus c squared. So why is this a classic application problem that you encounter in this section? It's because of this projection stuff. It's nice to see the projection stuff in action and actually being useful for something. In terms of actually going through and doing the problem, once you've derived the formula, the problems themselves are kind of trivial. Let's go through and do one. Find the distance between -6, 3, 5 and the plane x minus 2y minus 4z equals 8. And let's just again recall our formula. What was our formula? Our formula was this, right? This is going to be the comp. This is the distance. The distance equals this, which is equals this, which equals this, this, and this. All right, so this is the formula right here. So we want to go through and calculate ax1 plus by1 plus cz1 minus d divided by the square root of a squared plus b squared plus c squared. This is the distance between point and plane. Okay, so let's go ahead and just take all that and just plug it in. All right, so the distance is going to equal, so we've got a. What's a? A is so a, b, and c come from the normal vector to the plane, which the components are here in front of x, y, and z. So a is 1. So we're going to get 1 times -6. And then plus b. B is going to be -2 times y1, which is 3. And then plus c. C is going to be -4. And then z1 is going to be 5. And then minus d, which is 8, all over the square root of a, b, and c squared. So again, a is 1, so we're going to get 1 squared, -2 squared, -4 squared. And so what are we going to get here? This is -6 minus 6 minus 20 minus 8. And then we're going to have the square root of 16 plus 4 plus 1. That is 21. So this is -40 over the square root of 21. In terms of if you're actually doing a problem like this for a homework assignment of some kind for some class, often because it's a distance, they make it positive. And so in this case, this should be a positive 40. They just throw absolute values around here. I just forgot to put them in earlier. Okay, and so there's your classic application problem. That closes out the lines and planes section. Whew, it's a monster, these two videos. Thank you for watching, and I'll see you next time.